One, and we're live.
Good morning, good afternoon, everyone, to the 2020 Hot Water Forum virtual. This is one of 4 sessions we have on multifamily hot water systems. We had originally planned to have 5 out of 6 sessions devoted to this topic. We ended up with 4 in the virtual conference. I'd say we did pretty good. Why multifamily hot water systems? Well, they're the biggest deal that's currently going in hot water right now. They're also, for central systems, some of the most confusing systems to design and build. Many of the rules we all thought we understood for designing hot water systems are different here, at least enough to drive everybody a little bit crazy. And today we have 4 different presentations with 5 presenters talking about what's going on from their perspectives in this space. I'm Gary Klein with Gary Klein and Associates. I'm the moderator today. With that, I think we should just keep moving along. Some basic ground rules. If you have clarifying questions, please put them in the chat bar. We will look at them and read them, and we'll attempt to answer them in real time. If you have questions that you want to explore a topic with the presenters, please hold those questions till the Q&A session toward the end of the presentation today. Thank you. All right, let's keep going. All right, platinum sponsors, Ream and A.O. Smith. We want to thank them very much. They've been supportive for many years. We have silver sponsors, Bradford White, MIA, SoCal Gas, and Jackson EMC. Again, longtime sponsors, and we really appreciate it. All right, the first presentation is called Updates from the Coasts. We have 2 folks for this presentation. Nicole Cece, who's a mechanical engineer based in New York City, and Sean Oram, Director of Engineering at Ecotope out in Seattle. They're going to give their perspectives on hot water and multifamily right now they have a shared presentation. All right, Nicole, I think it's up to you.
Thanks, Gary. So, electrification of domestic hot water, it's gaining bigger footholds in coastal cities and in progressive cities. And so Sean and I today are going to talk about some of the progress that we're seeing in some of those cities today. So our focus areas are going to be the Pacific Northwest, New York City, and California. Neither of us believe that major decarbonization is going to happen without legislative pushing and support. Support and all 3 of these focus areas that we're talking about today have really seen a lot of progress with clean grid mandates and that kind of legislative support that we think is so necessary. New York City, where I'm based out of, also has an 80 by 50 commitment, which is an 80% greenhouse gas emissions reduction by 2050. The technical challenges that Sean and I see in both of our areas of focus are also pretty similar. We're kind of running into a lot of the same technical barriers on both coasts. And the market transformation challenges that we're running into are also similar. We all really need a lot more design and execution support, more cold climate products to use and choose from. And a big thing is for contractors in both of our markets to really take the fear factor out of the pricing and bids that they're giving us. Okay, so diving into each coast. I'm going to start with the East Coast. I'm based out of New York City, as Gary said. And East Coast perspective today, I'm really going to focus on New York City, just because we don't have enough time for me to kind of move around to some of the other big cities. And in New York City, I'm really going to be focusing on our larger buildings from an existing building retrofit perspective. And one of the big reasons for that is because New York City alone has over 1 million buildings, and more than 90% of the buildings that we have today are expected to still be existing in 2050. So retrofits are a big deal for us. Legislation to support domestic hot water electrification and decarbonization is somewhere where we show up pretty well. I'm going to start with the good things that we're doing and then kind of shift into some of the more problem areas that we have. So New York City's Local Law 97, big deal for us. That law sets carbon budget limits by building type. And starting in 2025, our buildings are actually going to start getting fined for exceeding their carbon emissions budgets. Those budgets are expected to ratchet down over time, so it's going to get harder and harder to meet those caps without doing real work. This means that Local Law 97 is kind of effectively a carbon tax. It's pushing buildings towards electric solutions with a financial signal in the market. Other legislation, New York State law is calling for a clean grid by 2040, and cleaner electricity coefficients from that grid getting cleaner are also going to be then reflected back in our Local Law 97 calculations. Now, we've also tried gas moratoria, and we've had mixed results there. We've had different moratoriums on and off for the last roughly 12 to 18 months. And unfortunately, a lot of our local developers started scrambling for oil solutions when they were told they couldn't get gas. So figuring out how to use gas bans, moratoria, any kind of pushing in that area is something we need to do more work on. And lastly, from a legislative related perspective, we have a new stretch code as of May 2020. It has some requirements for heat pump water heater minimum efficiency, but it still doesn't really address our big buildings and our commercial grade systems that robustly. Up until very recently, we haven't really had a lot by way of incentives. We haven't had really any off-the-shelf incentives for smart domestic hot water electrification projects. Everything has been subject to really custom one-off applications. It's been really labor-intensive to try to get any funding for that work. Just in the last couple months, some potentially really important incentives have come through, and we're really excited about those. I have to give the caveat that this is all brand new, and we still don't know how easy it's going to be to get those incentives and how accessible they really are going to be, because it's just really brand new. Now, where we do not shine is our expectations for return on investment for our projects. New York City is a finance city. Many of our buildings are owned by incentive group or by investment groups, by folks that are expecting market level returns. Some of my clients, they want nothing worse than a 6-year payback on any type of efficiency work. Our new incentives are going to help with that, but it's not enough to hit that kind of really tough expectation for really fast payback on capital work. Some of our building owners are factoring in energy savings and as a net operating income savings, and then using that to increase their building's asset valuation. But a lot of owners that we work with don't do that math. And electrification, it might not even result in real savings when you look at New York City's utility rates, which is what I'll get into in the next slide. Another side of this same issue is that a lot of owners often want to put their capital into something like a lobby renovation that's going to gain them a more predictable increase in asset valuation instead. So I mentioned our utility rates make this very challenging. We have expensive electricity and pretty cheap fuel, especially when we're talking about fossil gas. The bottom of this slide shows what kind of spread we typically see in our utility rates. And air source heat pumps in a cold climate like ours, they just don't have the kind of COP that it would take to overcome these rate spreads and really generate attractive project economics that our clients, a lot of our clients, are expecting. We also have extremely complex utility rate structures when you compare to a lot of other markets. No matter how hard you try to really calculate a project cost impact that uses time of day rates or leverages load shifting, with New York rates, you're probably going to miscalculate. It's extremely challenging to navigate. And lastly, when it comes to our utility rates and structures, our gas grid is very strained in some places, and our electric grid is very strained in other locations. And the benefits of reducing gas usage or smoothing out electricity and kind of leveraging that grid in times of low loading, those benefits aren't passed back to users very well in our market. And that lack of a feedback loop really does us a disservice when it comes to supporting the financials of these kinds of projects. So New York has taken some big steps to pushing decarbonization, but clearly we still have a lot of big barriers to address. And so I wanted to follow up here with just kind of giving an idea of what some of the work that my company is working on and that what we're trying to push. So we are working in New York City with the Mayor's Office of Sustainability. We're working to inform the city's carbon goals. We're working with utilities and state agencies to help grow incentives and build markets for this kind of work. We're also working with those same partners and with a variety of different manufacturers to bring more cold climate heat pump products to our market. Our first big buildings with air-to-water heat pump installations are they're actually in construction right now. So we have a couple of large buildings that are electrifying their hot water in the Bronx. That construction is expected to be done at the end of this summer. And that's kind of, those are pilot projects, really kind of showing New York City that a large building can electrify. And finally, we're working on tackling this issue with electrification financials not looking so great by investigating different scalable templated displacement strategies. Displacement with heat pumps, not completely replacing an existing fuel-fired plant, but displacing load gets us a foot in the door, and it's a lot more cost-effective in terms of invested dollars per ton of greenhouse gas emissions avoided. And when we do this math, we're also making sure that our clients really understand the Local Law 97 carbon penalties and are really factoring that into their financial modeling. So with that, I will turn it over to Sean to talk about how things are looking on the West Coast.
Great. Thanks, Nicole. Hi, Sean Orem with Ecotop. I'm going to fill you in on some of the work that's happening now on the West Coast. So kind of big picture, where are we trying to go with this entire sort of movement and transformation? And really, where the big focus is on the West Coast and some of the initiatives I'll talk about are really sort of focused around these points here. And so what we're trying to do is essentially make heat pumps the standard practice for hot water, for central hot water. What we're also trying to do is to deliver system seasonal COPs of 3.0 or better. And some of those comparisons that Nicole mentioned, this is, having the performance up at about a COP of 3 levelizes the operating costs for a lot of different climates. And so that's been the focus sort of on the West Coast. That's sort of the magic number. And that includes both the temperature maintenance and the primary plant and all the losses. And so that's a COP that we have been able to achieve in Seattle, all in seasonal. The next thing is alignment with EPA phase out of refrigerants, so low GWP refrigerants. These systems need to be more accessible, more plug and play, simpler. They need to be cost effective. Right now, there's a lot of bids are coming in, and they're sort of balancing the risk associated with these new systems. They need to be reliable and redundant. So we've got to have the same sort of strategies we've all kind of grown up with our central gas systems. And then the real crux here is the ability to load shift. This is the real value to the utilities and to kind of the future renewable grid, is we've got to be able to move these loads around. And so hot water has been identified as one of the major end uses that we can shift. Little overview of the legislation's codes. As Nicole mentioned, we've got similar carbon goals. Vancouver, I've sort of included in the West Coast because they're on a similar path as sort of the three main states on the West Coast. But City of Vancouver now, high rises have to be electric to get a permit. So that's a big change in Vancouver. They've got greenhouse gas emissions targets. They've also got a BC Energy Step REACH code. So REACH codes are a nice strategy to kind of get the markets moving. In Washington, similar, carbon neutral by 2030. One big change in Washington is that the performance modeling compliance path is now carbon based as opposed to cost. That's a big change. Also, come February 21, apartments have to have central heat pump water heating systems. Gas and electric will not be allowed, and that's in 6 months from now. It'll be really hard to get a permit in Seattle using gas, and that's sort of part of the big transition. And then load shift is really important in winter mornings. So it's an opposite problem of California that has an afternoon peaking. Similar as we go down the coast, similar targets. California leading the big push. They're trying to be carbon neutral by 2045. They've also made a big change in Title 24 from gas to heat pumps for hot water heating, so getting heat pumps into the modeling software. There are about 20 plus cities that have gas bans for new constructions, and so these are the cities that are really sort of scrambling to kind of put all electric, high efficiency, Title 24 compliant systems in. And right now, incentives are being developed for high performance heat pumps, both the heat pump water heating systems as a load reduction, as well as load shifting. So there is investment happening in the development of the heat pump water heating market. Some of the incentives. So incentives are somewhat short now. Most of it is just modeled savings. Seattle City Light, which is an electric utility in Washington, is offering a $350 or a $500 per apartment unit for central heat pump water heaters. So that's a start. We're seeing incrementals still higher than that in this sort of early market. And there's, each of the states kind of positioning for different incentive levels. Again, getting back to kind of the need to create shiftable resources. This is a picture of kind of the Cali grid, and I'm not expecting you to dive in, but these are all 12 months, and you can see these different colors represent different rate times, so different uses of energy. And so the game really is to be able to create these hot water systems and move them around so we stay out of these peak conditions. This is sort of where everything is going as far. So what we're really trying to do with these hot water systems is enable electrification of heating systems as well as EVs. So that's really the kind of the bigger picture goal here. Again, this is the classic California duck curve. A lot of solar in the day has driven down the load, and then the gas turbines have to ramp way up. And so in the future, part of the kind of vision here is to stack up renewables and storage, and then that peaking ends up being is done with storage. And so we can consider storage both battery storage as well as thermal storage. So that's sort of the idea, is to move the loads from the head to the belly of the duck. Another big movement that's happening on the West Coast is the Advanced Water Heating Initiative. We are supporting the Central Heat Pump Water Heating Initiative, or the Central Heat Pumps Working Group under BPA's direction. And so this is really getting a bunch of different utility folks and a bunch of different research folks together to try to consolidate resources and really be working on the same thing, because everyone on the West Coast, it appears, has the same goal. We're all trying to kind of move to heat pumps. Another piece that Ecotope, as well as the Advanced Water Heating Initiative, has been focused on is this idea around the technology innovation model. And really what this is designed to do, it's sort of a methodical approach to getting new technology into the market, making sure that manufacturers know what's going on in the market and vice versa, and really getting the manufacturers up to speed to really So that's been a big focus on in terms of the Advanced Water Heating Initiative. So what are we doing about it? I'll show you sort of three things that we've been focused on. The first is to try to develop plug and play skids or packages from the manufacturer. So below you can see in this slide, we've got this is a 100-unit sand and skid, and so we're working with sand to develop these packages. In California, most of the hot water plants go on the roof, and so we've got a skid of tanks and a skid of heat pumps, and the package is fully integrated. There's controls, everything is there. You hoist it up to the roof, and away it goes. This system will be designed to operate for 16 hours. It will not operate during the peak from 4 to 9 p.m. So this is an exciting project, but we're building a bunch of these for projects in Menlo Park, which has banned gas. We've also got what we call the EcoSizer. This is a sizing tool. This has been funded by the Advanced Water Heating Initiative, but this is really a way to really start to look at how to optimize the size of these systems. Without this optimization, you're gonna oversize your systems, and so what's really important is to get the sizes right so that we can stay cost competitive with kind of the base case approaches. Third piece is sort of continuing to develop the HIPWA-SIM. HIPWA-SIM is really the backbone to central heat pump water heating simulation in California, a program called CBEC-RES. And so we're working on adding additional manufacturers' data and also experimenting with load shift and how that impacts the plant size. Looking ahead, we're looking to kind of develop a more complete design tool that can answer the energy question, and so we can give energy use feedback to designers and utility providers. Temperature maintenance is still an area that needs a lot more research, so that's another focus. We need to continue looking at that, at how to optimize, and we'll see more of that later on with Gary and Pete. And we just need more research on load shift and how to integrate the systems, and working with the manufacturers to bring the low GWP products and get plug-and-play packages to the market. Again, also persistence studies with pilot projects are really important to understand the long-term effects. Again, training is sorely needed, and so this is becoming a focus on the West Coast. And developing incentive programs and codes to help with these sort of initial early market costs. And that's the end.
Okay, this is Gary. I'm back again. I think in the interests of time, we're going to move forward, but there is one question that came up that I think that I'd like both you and Nicole to go after, which is from Stephen Memory with A.O. Smith. For New York City, and you can answer for the West Coast too, are these fully electric buildings using heat pumps? That are using heat pumps, are the heat pumps outdoors or indoors? And if outdoors, are they designing the heat pumps for the whole load or using backup at lower ambience?
Sure, so I can start with the New York case. When we are looking at electrifying the entire building's domestic hot water load, those heat pumps are going outdoors. We do not have, especially in the multifamily sector, that many buildings that have large enough internal gains for it to make sense to have those heat pumps inside. I do have one site that's on the Con Ed district steam loop, and they have a lot of heat loss off that district piping, and it actually does make sense for them to have some heat pumps indoors to harvest that, but they're only looking at displacing about 50 to 75% of their domestic hot water load, and it's a low load. So most of the time we're looking at plants outdoors. We started off kind of trying to attack retrofitting 100% of the domestic hot water load, and we just found that the cost per unit of carbon abated was so much higher with that approach than it was with a displacement strategy. So now we're actually looking at more templated, scalable displacement projects to really kind of get more market saturation of heat pump water heaters, just period. Before we start worrying about taking on the entire domestic hot water load. But in that case, we are also still just looking at putting those heat pumps outdoors.
Sean, West Coast. Sean, I think you're muted.
Thank you.
This is Pete.
Sorry. Just to answer that question about covering the load, all of our designs cover 100% of the load, both the primary water heat as well as the temperature maintenance. I think we've designed around 60 of these, and we have a pretty good idea of what it takes to kind of do the whole load. And like I mentioned, this is essentially code in Seattle in 6 months, and we've got the start of a market developed there, but it's taken a while. So, but anyway, yeah, that's the answer there. And yes, the heat pumps are either outside or in the parking garages, subgrade. We get better performance because we don't see the peaks.
Great, thank you. We're going to move on. I know there's a couple of questions come in, and we'll get to those during Q&A. If you guys would look at the 2 questions that just came in, I think you may be able to give a written response. All right, with that, we're going to move on to the next presentation, which looks like it's going to be Peter Skinner, who's our next speaker. Pete is an engineer from upstate New York, Albany area. Used to work in government for a state office and decided to become a solar contractor. Now he does hot water systems for a lot of multifamily in upstate New York. Pete, it's all yours.
Thanks. Did everybody hear me?
Yes, I can hear you. You need to push the slide that you want us to see. There you go.
Okay. Well, again, this is great pleasure to be on board with such a great crew of people. I'm in the upstate part of New York, and it's a little cooler than it is in New York City. I've been experimenting with solar thermal systems coupled with air-to-water heat pumps located outdoors. But unlike the West Coast, where Sean is, we have cold winters. And we need to use our 410 air-to-water heat pumps with antifreeze to make this system work. I'll be having data in a year or so about their performance, but over the last winter, they worked pretty well and backed up my solar system. And then in the end, we had electric resistance for the final push to the temperatures necessary. My background is in civil engineering and advocacy for environmental improvements. And only recently did I really get a great gig, and that was being a solar thermal guy. I started after I graduated from the Attorney General's office to work on plumbing and on solar. Mostly solar to start, but that got me certainly involved with plumbing. And, that's where I feel most comfortable right now. I just want to make sure everybody knows where I'm going to try to get to by the end of 15 minutes. And there's a plumbing revolution here, and it's happening right now. We are actually making bigger pipes smaller. We're making compact networks that are much more sensible. Our practically perfect plumbing, that's a Gary term, can save energy, the install cost, the water, and get hot water to the tap faster. And it really works. Pipe sizes really need to be based on what real water draws are. And how do I know what they are? We have a whole new way of monitoring real demands, and I'm going to tell you about it. When I graduated from the AG's office, I got into solar thermal work and wrote a textbook about it and installed about 50 or 60 custom systems when I got this opportunity to work in the net zero multifamily arena. And that's where I put in 26 systems on 13 buildings. One of the first buildings, I was sitting in the mech room with the GC and said, I know this guy, Gary Klein, or at least I've read about him. And he says we ought to be using 3H PEX home run twigs to every fixture. And he said, hey, that sounds good to me. Do a little analysis, which I did. And bingo, that's what we put into Net Zero Village. It's an award-winning project near Albany, New York. And after it, I got the solar systems to work, I got out my Fluxus ultrasonic flow meter and started to measure flows. And lo and behold, I found that the flows that we were seeing at Net Zero Village were really small. And that's what I thought I ought to call Gary up and talk to him about. And the rest is history. We've been talking for about a year now, and I've learned a tremendous amount. And really, in recognition of what he's been able to do, I want to say thank you, because, you know, I'm up to about 1% of what he already knows. And maybe by another year, I'll be up to 2%. So we're very lucky to have him, advocating for change. And I hope to be one of the change makers. One of the ways we do make change is to try to figure out how much flow real buildings are using. I use my little flow meter down here on the right-hand side, and that's Hugh Henderson, who's developed a very excellent magic box, which gets us 4 ultrasonic sites and 4 NIST quality temperature sensors. There's a data cache on board and a communication system that goes up to his automated stats generator, and we get some amazing data from these buildings that I'm now monitoring. And we're finding all kinds of interesting stuff going on. I think it's a tremendous tool, and will be helping everybody know more about their systems as a result of our research. For instance, at Solara, which is another net zero building that I did the plumbing for, we've been looking very closely at the flows. And it's probably hard to see, but on the left-hand side, you'll see on the y-axis, you're going to see 2, 4, and 6 gallons a minute. These are 24 apartments. And you'll notice that most of the time, maximum flows are around 2 gallons a minute. A little bit of simultaneity, but not a whole lot. This is mixed occupancy. This has families, young kids. It's got professionals, tradespeople, and a bunch of seniors. So you see a very mixed pattern here. And this was just 2 or 3 days ago. So this is real life in the lockdown of upstate New York. Now, here's a place that I looked at, 35-unit senior housing out by Utica. And you might be able to see here from the cumulative frequency distribution that 99% of the time the flows there were below 2.6 gallons per minute. Now, do you need a 2-inch pipe for 2.6 gallons a minute? The answer is no. And here's some numbers for down here in the red box for Solara, the B4, which I just talked about. There, with mixed occupancies, we're only seeing roughly 4.2 gallons a minute at the 99th percentile. So we're not talking about large flows that you need to design or choose your pipe size for, even in the COVID times. So Gary's idea about 3/8-inch home run twigs seemed great to me, but then I was a little worried that the pressure loss would be too great. But I did know that our fixtures were small flow fixtures for the shower and for the kitchen sink and certainly for the lavatory sink. And so I did some calculations, and this dotted line shows the arrival time of the hot water. Now, it's a little slower than that, but it's pretty close. 5 seconds at 1.75 gallons per minute is what I could expect out of about a 30-foot PEX twig or whip out to a fixture. And how much pressure loss would I lose? Well, from my actual measurements at 1.75, you're looking at about 12 PSI loss. Well, if you got a lot of pressure in your system, who cares about 12 PSI? No big deal. Where we are, however, we are in an old municipal system, and we're starting out at 45 PSI. So this was really important. But through other optimization approaches, we were able to make sure that people's showers were just fine. And here's how my layout for the next phase is, or at least was supposed to go. You start with a mech room right here in the center of a long, fairly narrow building with the 1-inch PEX trunk winding its way down the hall, turning around to 3/4, and all the way it encounters 5 nodes of manifolds with individual twigs going out to fixtures on all 3 floors. So one trunk line goes to serves all 3 floors of this particular building. And then there's the hot water return over here back to the tank for recirculation. And the way we do recirculation is really simple. Right now, it's 4 minutes on, 20 minutes off. 4 minutes more than refreshes the whole line, and the losses because of recirculation are much, much lower. Now, that's not exactly what happened. As you can see from here, we got a straight trunk line and a straight return. But that's the plumber doing his thing. This plumber liked it straight, and that's what we got. So sometimes it's you got to work as a team and accept the way the installer wants to do it. And this has worked tremendously. Here's a picture of the manifolds here. A very small branch off a 1-inch trunk. And here's your twigs. These are hot water twigs going through a conduit on the firewall off to individual rooms and fixtures. I'm sorry. And over here on the right-hand side, here's the cold water distribution system. I didn't design that. The plumber did, and I was really delighted to see he used short branches through the firewall and then to a manifold with individual twigs to each fixture. So I think he's gotten the message. It makes me feel good. But Gary has said one important thing. It's not so much about just the pipe size. It's about coming up with a way to minimize the volume of water upstream of the fixtures. Use small diameter feed and trunk lines, short branches, size the manifolds properly, use your home run fixture specific 3/8-inch twigs. What great things happen? Well, you get less embedded carbon and material involved. You get it installed really fast, fewer connections that can leak. You get less water in the pipe inventory. You get less energy and water waste, faster hot water arrival, faster tubing velocities, keeping bacterial buildup lower, better balancing. Man, it's great. And then lower recirculation volumes. So it has a lot of good things to say for it. And I'm really proud to be part of the group that makes this happen. How come you get bad distribution networks in 2020? Well, the standard codes have elements that require fat pipes. The water service fixture unit approach really predicts high simultaneity and consequently fat pipes. Even the UPC's Appendix M optional guidance comes in pretty high. You'll see that in a minute. And very few people are actually building plumbing designs on real flow data. I think that should change. And architects and mech engineers need to talk to us out there in the field and in the mech rooms, coming up with the real numbers. So if you look in general, the water service supply fixture unit approach is pretty old now. Gary says it goes back to before I was born, and that makes it really old. And consequently, it reflects estimates of large fixture uses and high simultaneity. That's not really the case anymore because fixtures are much more careful with the water use. And Appendix M has made a big improvement, and you can reduce pipe sizes, 1 to 2 nominal sizes. And here's that water demand calculator that you can use at this website.
A quick time check. Pete,
yes.
Quick time check. 5 minutes.
Okay, no problem. Here's what Gary calculated here. Let's go to 20 units using the WSFU approach. 56 gallons a minute for a 20-unit multifamily. Holy moly! No wonder they proposed 2 inches. The Appendix M approach is smaller, cuts that right in half, and that's better. But that's a far cry from the real numbers that I showed you before of 2 and 4 gallons a minute. So we were asked to look at a building out in Utica. Here is what the old school design was, circa 2.5 to a 2-inch trunk and a 2-inch across the 3rd floor ceiling with risers dropping down to hot water return piping to the tank. This requires, in order to keep these piping refreshed, almost 7 gallons a minute continuous to keep this refreshed. The hot water, the heat loss is significant as a result. We worked together with a team, and including the plumber, to come up with a much simpler design. A single loop going across the first floor and then up to the second floor ceiling and back to the recirculation here. Simple, with short branches and manifolds. And that is being it's being installed as I speak. This is a 35-unit building, and 2 more will follow with this design. It can be done. We were able to reduce the number of big pipes, or the footage of big pipes, substantially, and I can describe that in more detail. I want to finish by showing this is installation of home run twigs here. You get a big roll of 3/8-inch tubing, stuff it down the hole, it goes through the truss work and comes up at the fixture. It takes about 2 minutes maximum to pull a single fixture, and the result is a manifolded approach. This is Viega, 3 twigs. This goes to an individual apartment. 3 twigs for hot water, 4 twigs for cold. So I just want to remind everybody, there's a plumbing revolution going on. Small pipes are in, fat ones are out. Make your layout compact, it's sensible, and we can save money installing it, less leaks, save water, and get water to the tap faster than ever. Pipe sizes should reflect what real draws are. We've made it work, and others too. Thank you a lot.
Thanks, Pete. We're going to move on because of time. So Emily Higbee is up next. Emily is the research director and energy analyst at Redwood Energy and studied at Humboldt State University. She's doing a lot of work on domestic hot water use, building electrification, and resilient home design for extreme weather climates. Emily, it's all yours.
All right, so the goal of my presentation today is kind of to touch on some of our field data that we're observing from a grant project that we've been working on, and compare it to CBAC Res, which is the building compliance modeling software we use in California. It's been a few-year process, very much team effort, so shout out to the team here, and then also for Greg for helping with some of the data analysis for this presentation. So the focus of our grant was to demonstrate zero net energy design at 4 project sites in California, also with a focus on demand side management of the hot water systems, all to inform best practices, codes, and standards. In particular, that's why we're interested in CBAC Res, to see how our compliance modeling matches to what we're seeing in the field. And bigger picture, why do we care? Hot water can be the largest load in a zero net energy multifamily building. So making sure we understand how much energy these systems are using so we can offset them with solar. We also care about decarbonized design. Heat pump water heaters will play a big role in switching away from gas, like we heard earlier from our presentations. And we care about the model accuracy, how much water is being used and when, and how efficient are the heat pumps being modeled. And part of this project was to look at thermal storage as well. So eventually, this is kind of an ongoing comparison that we're making here. Like, how does the software match the thermal storage we see in the field, looking at the energy savings, but also potential carbon savings as well. Brief overview, these are our project sites. They're all affordable housing, 3 of which are farm worker housing, and 1 is just families, and that is Benner there. So this is Calistoga and Cloverdale. They use the AirMex for heating, cooling, and domestic hot water. As it stands, the software does not model these kind of systems, but so my focus was not on these projects necessarily. Benner uses 2 central gang sand implants with an isolated recirculation loop. And our goal is to compare to the central model that's in CBEC Res now. It's relatively new and it's being developed further. And then, so the focus of this presentation will be on Atascadero. So at this project, there were ream individual tanks, 50 gallons for the 2 bedrooms and 80 gallons for the 3 and 4 bedrooms. Yeah. So a little bit more about CBEC Res. Like I said, it's used for compliance modeling, and 2 important components inside of it are the draw profiles that were modeled specifically to represent realistically how draw profiles are observed in the field. So we'll take a closer look at that. And then also within CBEC Res is the heat pump water heater sim algorithm developed by Ecoto, and that, as it stands now, is for the individual tanks. So just a brief overview of our water use at all the sites. The average daily hot water was in between 56 and 67 gallons per unit per day. And then the average daily gallons were range from 14 to 20 gallons per person per day. And this is a little context. How does this compare to other leading studies? This is like for the average occupancy. This is the gallons per household per day, per unit per day. And as you can see, it's similar to what others have observed in the field. Particularly, the blue line is the residential end uses study that was finished in 2015, and we're around the same use per unit as that study. So again, a deeper dive into Atascadero. This is what the water looks like per bedroom. So at the smaller bedroom sizes, our averages matched what the software was telling us. But at the higher or the bigger bedrooms, our averages, there's more variance and it's a little higher than what CBEC Res is saying. These next 3 graphs are looking at the individual units that are contributing to those averages. So as expected in the field, there is more variation, and in CBEC Res, it's more consistently modeled. The max values coming in at around like 115 gallons per day per unit. Going on to the 3 bedroom, again, more variance in the field, and the max values for CBEC Res are around 115 still, but you can see in the software it starts throwing in higher gallons per day values. So the draw profiles are getting spikier as the bedroom sizes increase. And then finally, the 4 bedroom in the field, we saw that there were a few high users adding to that average. And yeah. So just to explain a little bit about the draw profiles in CBEC Res, they are dictated by the number of bedrooms, and there's five unique profiles. So from studio to 5 bedroom. And as you add more units in the software, it's the same draw profile for all the 3 bedrooms, but they shuffle the days to have more variation in the draws and the spikes there. So as you can see, they're relatively consistent, but they do vary a little bit. And the overall totals are the same, shown here. So this was trying to get at monthly variation in the software versus what we were seeing at Atascadero. We were seeing a little drop in energy use, or not energy use, but water consumption in the summertime. And as you can see in CBEC Res, there's not really a monthly trend there. One thing to point out, again, this is...
Emily,
yeah.
We have a clarification question.
Sure.
Did you say that the Atascadero site is farm worker housing? And is it possible that water use of this group is different from other populations?
Yeah, so Atascadero is farm worker housing. And yeah, we could assume that the water use is different. So we do see a higher occupancy, and I have some graphs of that later. But also, I think what we were seeing that they tend to wake up earlier too, and I think come home a little earlier. And I know Greg on our team has done a deep dive into that as well. So yeah, they do use water a little bit differently. So yeah, this is the monthly variation again. CBEC res is relatively consistent across the different months. And then in the field, we saw a little drop in the summer months. So this is next few slides are going to touch on occupancy. So we know water use varies by occupancy, and it's not typically a input to the software, but understanding it is important. And yeah, and at Atascadero, like I just said, we were seeing higher occupancies. So what is the occupancy in CBEC res? I know this is a little busy, but in the 2, 3, and 4 bedrooms here, this shows the percentage breakdown of occupancy. Just pointing out the 4 bedroom here at Atascadero, it's spread out mostly for 4, 5, and 6 occupancy. And in CBEC res for the 4 bedroom, it's spread out between 1, 6, but mostly in the 2, 4, and 6 occupancy. So we are seeing higher numbers there at Atascadero.
Emily, a time check. We have 3 minutes to go. We have 3 minutes.
Cool. I'll go quick. The last few slides are quick. Yeah. So how does our occupancy compare to other data out there? So Atascadero is this red dashed line, and CBEC res is the dotted line here. So we are a multifamily affordable housing, and it does match more like what CTAC says for affordable housing. So that's interesting to see. And the last 2 graphs are going to talk about hourly consumption. So in CBEC res, there is a higher morning peak and an evening peak as well, but it's definitely higher in the morning. But in the field, we're seeing a trend towards an evening peak, which is interesting to observe. Might have some effects on time of use as we move forward. And lastly, what Pete was talking about, what are the highest draws? How often do they happen? So the top here is Atascadero, and the bottom is CBEC res. So CBEC res actually matches what we were seeing in Atascadero pretty well, where 90% at Atascadero, 90% of the draws were under 7 gallons per hour. And in CBEC res, 90% were under 8 gallons per hour. So that was interesting to observe as well. And that's the last one. So a little bit of review. This is an ongoing study, and we are finishing up our grant work. And a few of us will be presenting at the summer study, other people in our team. So you can look forward to that. But overall, water consumption on average was a little higher for bedroom size at Atascadero, likely due to the higher occupancy. Our hourly consumption tended towards the evening. Some peaks were higher for Atascadero, but 99% and 90% were in the same range. And for future work, we're going to look a little closer at the seasonal variability and look closer at incoming water temperature and the effects of ambient air temperature. And then also we want to look at overall energy use as well, which I didn't really touch on in this presentation. And that's important for, our baseline performance, but also our thermal storage operation as well. And with that, thanks for listening.
Thank you, Emily. I'm going to move to the last slide because we only have about a minute left. We've tried to answer most questions during the chat when in the window. We are moving over to the chat room right now. It's on the Zoom. You all have access to that if you choose to move. Here's some upcoming events that ACEEE has going on. And I think with that, we're going to stop this and move over to Zoom. That'll be the best place for us to hold the next bit. Thank you all very much for attending, and I look forward to participating in the chat room. Bye now.